What are we now? Session 8? Welcome to session 8. Our topic for this session is evolution from the diffuse to dense OH, clumping, and H1OH mixing. I'm looking down the list. I don't think there's anyone in here who gave me an introductory slide that we haven't already seen, so we might just fly past that bit and go straight into the talk. If you're ready, Ningyu.
Yeah, sure.
Awesome.
Can you see my slide?
Yep. Yep.
Okay. Okay. Hello everyone. I'm Ningyu Tang from Anhui Normal University. My topic is about the evolution of OH from diffuse to dense regions. The previous speakers has talked a lot about the OH history. It was the second detected molecule in ISM. The first is CH. But OH is the first detected molecule in radio band. Since the OH detection, we do not have a lot of studies on that, because the OH emission in radio band is very weak. It's around 20 micron kelvins. But at 2005, we realized that the problem of dark gas. The dark gas cannot be traced by H1 or CO emission, and the dark gas mass in the Milky Way is comparable to the molecular ones. To solve this problem, we need to find another process of molecular hydrogen. So OH is a best candidate, since the OH is participate in the CO formation, and the position of the OH it locates in it exists in the CO3 molecular regions. So OH is the best candidate for tracing molecular hydrogen in diffuse molecular gases. In 2017, we have conduct OH 18 centimeter survey towards 51 satellites of GOT-C+ projects. Finally, we detect 7 CO dark gas components with both C+ and OH emission. As you can see in the lower right plot, the C+ intensity seems to have a linear correlation with OH column density. But OH emission is not a good observation. Since there exists the problem or the degenerate problem of excitation temperature and optical depth. So to solve this problem, the combination of OH absorption and emission, it can solve this problem. In 2018, we used the Arecibo telescope. We finally detect OH absorption towards CO dark molecular gas. And based on this data, we have direct measurements of both excitation temperature and optical depth. This allows us to have precise measurement of OH column density. And I think the previous speakers, especially Michael, they have showed the results. Show our results in the last section. Since we have Sorry, hi.
Hello, yeah, I think we can hear you now.
Sorry, I don't know why it exists a few seconds ago. Can you hear me?
Yep, we can hear you.
Yes,
Would you like to send me your slides and I can share them?
Uh, can you see my slides now?
Nah.
No. Okay. How about this time?
Yep.
Yeah. This slide is
Yep.
this slide. Okay, so we have we found the OH excitation temperature. It follows a log normal function, and it peaks at around 3.4 Kelvin. For the OH abundance, so we they have he have already introduced the results. So it plots the OH abundance as a function of H2 carbon density. But there are large uncertainties in this plot. It's difficult for us to determine what's the relationship between OH abundance and H2 carbon density. Is this a flat or is it a increasing trend? So it's difficult. We need more samples. Michael they have other independent measurements of OH absorption. With this new data, they claim that it is a decreasing trend. So the OH abundance will decrease with increasing proton carbon density. But the OH carbon density they calculate is based on the assumption of constant excitation temperature. With OH emission, we Shudor and Dili and they have used a reversible telescope to observe OH emission across the linear boundary of Taurus cloud. They found a decreasing trend of OH abundance with increasing visual extinction. But this relationship can exist in denser regions. So to answer this question, we conduct OH emission towards 144 dense molecular counts. In this this is a result. We found a similar decreasing trend of OH abundance with increasing visual extinction, but we know that to calculate the OH carbon density, we adopt the excitation temperature relationship between with this equation, so that the difference between OH excitation temperature and the background temperature is around 2 Kelvin. Since we have H1 observation towards these dense clouds. The cold H1 gas in the dense clouds can be used as a to measure the cloud age. So we have the first time we measure the OH abundance as the dependence of cloud age. We compared the results with that from time-dependent chemical model. They have incredible consistent. The OH radial band is not the only observation it's not the only observation method to detect OH. OH can be also detected in UV band. As in Rollins' paper, they have summarized the 17 data points from the UV absorption, but they cannot find an obvious correlation between OH column density and molecular hydrogen column density. And the next question is, are the OH measurements from UV and the radial band consistent? I took experiment with Epsberg telescope. We observed OH emissions towards 17 OB stars with Epsberg. As for an example, towards this star, the color extinction is 0.27 meg. And the UV absorption gives a OH column density of 4 times 10 to 13. But with LTE analysis and the beam filling factor of 0.1, we calculate that the OH column density should reach 5 times 10 to 16. So there exists a large gap between the OH column density that's in both in UV and the radial bands. So we need more comparison observations to eliminate the gap between UV and the radial measurements of OH. OH is originates from the ionization of cosmic ray. So in 2 years ago, we used OH, CO, and HSO plus to study the cosmic ray ionization rate in diffuse clouds. In dense regions, the cold H1 gas originates from the cosmic ray ionization too. The cold gas can exist, it will shows a H1 narrow self-absorption feature in the H1 profile. In this case, OH emission is found to be coexist with Hinsar feature in dense clouds. By this right, we have further observations towards the B213 filament. We found that the OH is not consistent with the cold H1 gas in the filament. We cannot find any correlation. So we need more investigation is necessary to answer if OH trace cold H1 gas inside the molecular filament. So that is all, and this is a summary of my talk. So we found the OH abundance maybe it presents a decreasing trend with visual extinction, but the present data has very large uncertainties, and the adoption of excitation temperature is important for calculating OH current density in radial band. Maybe we need in the future we need the combination of observations and chemical models to understand the physical properties that affecting OH abundance. So I have two questions here for that is maybe can be discussed in later. So which is reliable? OH can be observed from UV, both UV and radial observations, which is reliable. So the second is, does OH chase cold H1 gas inside the molecular cloud? And what will affect this correlation? That's all. That's all. Thank you.
Well, thank you for that, Ningyu. That was so cool. Very interesting. Thank you so much. I have a lot of questions, but let's see if anybody else has any questions for Ningyu. Heap.
Yeah, actually, I have a few questions, and two of them are exactly the questions shown here on the screen. Yeah. So my first question would be the second one. You said that OH is not really consistent with the cold H1 gas or CNN inside the dense molecular cloud. Could you get back to that slide and could you yeah. Now the next one I think 16. Yeah.
Okay.
Yeah. Could you elaborate a little bit more about that? What do you mean about the inconsistency between OH and CNN in velocities, in spatial contribution, spatial distribution, or something?
Okay, so you can see in the top left figure that is the 13 CO. That's the intensity map of the 13 CO. So the 13 CO it has a consistent with OH, but for the Hinsa current density map, you can see here, you can see in the top right figure. So it's not always consistent with the 13 CO, but OH does.
So when you say, 'cause I was going to ask this question too. Thank you, Heath.
Yeah.
When you say it's not consistent, are you saying that are you referring to the color map that's on the right-hand plot at the top?
Yeah, yes, that's in the color map is Hinsa current density.
Hinsa current.
That represents the cold H1 gas.
Oh, and I see the plot that is then below that that's plotting individual what's that plotting? Individual sight lines or
That's great. We have great observations towards these filaments.
the grid, yeah. Okay.
Yeah.
I see. So that's where you're saying you don't see the correlation is that there's no trend in that plot there.
Yeah.
I
And I can answer the Heap's question with this figure. So it is not the cold H1 gas. It is not CNM. CNM exists in the envelope. The cold H1 gas is inside the inside. Can you see the black circle is inside the core? That's the cold H1 gas.
Well, in the core, I think is it not H1? Is it H2 and H? Is it something?
H2 and H1.
Oh,
So is that when you've got a trace amount of atomic hydrogen existing with the H2 because of cosmic ray dissociation?
Yes.
Okay. And so technically it should be present throughout the whole thing as well, right? Including in the kind of white zone where you've labeled it OH. So you've got the envelope and then the sort of a white bit, and then you've got the core.
Yeah. Maybe, but to represent that, okay. So the H2 should also reside in the black region, in the white region. So sorry.
No. I was just checking my understanding that there wasn't something special about the temperature in the core that would somehow be related to what you were saying. I had a question about the previous slide with the color maps on it. If you could
This one?
to the yeah. So how reliable is the identification of the Hinsa? Because I mean, how clean are the spectra? I know that sometimes looking for self-absorption features can be quite ambiguous. So I was wondering how, how that in that color map, how reliable is that as a column density map of Hinsa?
Yes, the derivation of Hinsa that it relies on the signal to noise ratio, and we use a function to smooth the H1 spectrum to extract the OH the Hinsa signals from the H1 survey data.
Okay, does it look clean though? I mean, can you see a beautiful dip, or is it something more like a little fluctuation in the H1 spectrum?
Oh, okay. Yes, they exist. Sorry, I didn't have a.
Yeah, it looks clean. Okay, yeah. So I have another question. So I can see from this that the Hinsa map does not well trace the 13CO filament either. But perhaps, so what would you expect? Would you expect the Hinsa to be following the dense molecular gas? Like, what's your expectation for the Hinsa distribution relative to the 13CO, first of all, so I can understand that?
Oh, yeah. This result is out of our expectation too. So maybe we will discuss with some chemistry researchers and to find what happens here.
And is there any ambiguity between Hinsa and envelope CNM? Because, I think I understand that Hinsa is defined as extremely narrow H1 self-absorption. So my questions would be, could it be mixed up in any way with the envelope CNM is one question. And then my other question would be, I suppose, could some of the Hinsa, the cold core H1 be missed because there is insufficient bright background H1?
We use the CO. We use the 13CO to trace the Hinsa. So, but sometimes they may mix with CM, but that is very cold CM.
But here the 13CO doesn't agree with the Hinsa. So how do you use it to trace it?
Sorry?
Oh, sorry. You said you used the 13CO to trace the Hinsa, but
Yes.
what your plot seems to be showing is that the 13CO does not trace the Hinsa. Am I missing? Maybe I'm misunderstanding something. Because you show this at 13CO filament, which is bright and thin, and then I see that you've observed it with those circles that are beams, but I don't. But as you've said, you're puzzled by the fact that the Hinsa distribution is very different to the 13CO filament.
Okay. So I use 13CO to trace Hinsa, but that not means that there will exist Hinsa there. because it's if there's a certain CO emission, but there's no H1 dip around the certain CO velocity, so there's no hints
Oh, I
there.
see. So you use the 13CO to decide where the hints should exist, I guess.
Yes.
Yeah. Okay. I'm trying to learn about this.
In velocity, I think.
Yeah.
So when you were looking at sightline by sightline, comparing the Hinset and the OH, did they match up kinematically? Because I think you had a plot, it might be on the next slide, I'm not sure, I'm a bit mixed up now, but is there a plot of comparing in velocity space on the next slide?
We have for the special solution, we smooth the 13CO to the beam size of OH, and for the kinematic distance, I did not show here, sorry, but we have a we have comparison between the OH and.
Ah, we've lost him.
Just at an important time.
I know. And he might not notice.
He's just talking still.
I thought he had there. Was it just my imagination, or was there a plot that had that beautiful little Hinsa dip and then an OH right underneath it?
I think that was a different source, possibly.
Was it? Okay.
I think so, but I could be wrong. What he's looking at now is part of Taurus.
Yeah.
And no, I don't know actually. I don't know if it's a different source. The signals and noise looked extremely good on that plot. It made me wonder if it was a model. But
yeah, right. Yeah, because I see that plot there didn't show any correlation between the OH and the Hinsa, like the column densities. But I wonder if kinematically,
yeah.
oh, he's back. He's back.
I think I missed, maybe Ningyu can enlighten me once the slides come back, but I think I missed why you'd expect there to be an association between OH and Hinsa in the first place. Was that like any
Sorry, my network is my connection to the Zoom is not stable.
Right.
Yeah, that's because at first we thought that OH and the cold H1 gas, they are all originate from the cosmic ray ionization. So you can see the the formation of OH. It is originates from the ionization of hydrogen or molecular hydrogen by cosmic rays, and similar in the for the cold H1 gas. It is also ionized, but it is also ionized by the cosmic ray.
Okay. I think I think that, sorry, Anita, you go. Yeah.
So that plot was the one that I was thinking of, where it looks as though the self-absorption in the H1 exists at the same velocity as the OH. Was that at least typical along these sightlines where they matched up in velocity?
For the 4 crowns, they are matched. Most of time they matched, but for this one, for this case, we cannot. That means we cannot find the match for all the filaments.
Okay. But when you did find a match, when you say finding a match, do you mean finding any kind of emission feature in the OH, or do you mean finding an emission feature in the OH that aligned with the velocity of the H1 self-absorption?
Yeah, so I mean the consistent OH emission with the H1 absorption.
Yeah, okay.
Velocity.
So there's a good chance that they are physically like coexistent with one another. Is that a reasonable conclusion to state that the OH and the cold H1 are mixed here? Even though there might not be a single like cohesive process that would then make their column densities proportional to one another, at least are they occupying the same space?
We don't know, but and possible explanation that maybe there's no warm H1 gas behind this filament, so we cannot see H1 absorption in towards this filament.
That's fair. Yeah, yeah. Beth, you have your hand up?
Oh, I've got a quick question. Did you look at C18O towards this filament, since that traces even denser gas?
C18O?
Yeah.
No, we have 13 CO.
Okay, I'm just, from my understanding, oh, Zoom is telling me to lower my hand. Okay. From my understanding, C18O traces denser gas than 13CO. So I'm just wondering if the Hintsa would agree with C18O more, like since it's even denser. Just a thought. Could be wrong.
Yeah. C18O can trace denser regions.
Yeah.
So that's a good idea. So we have new observations to detect more denser more denser tracers. For example, DCO plus. So we have a new observation towards other sources to check if the cold H1 gas traced by Hinsa is coexist with the dense tracers.
Could I ask, because that was, I believe that was your second question in your conclusion slide. Could I ask the first question?
Yeah.
About which one is more reliable, the UV or the radio? I to get to that, I was wondering, what exactly is the transition in the UV? Is that coming from the ground state going up? I can't hear you.
Here.
Yep. Yeah, I couldn't see which levels.
They
Okay.
can it's around optical around optical band. So it should be can detect by the ground-based telescope optical depth.
No, I mean so the excitation that you're seeing in the UV absorption, is that an excitation from the ground state up to some higher rotational level? Or what's the nature of that transition?
Okay, sorry, I do not have much knowledge about the electric transitions of OH.
Yeah, fair enough. I have no idea. But I guess what I was getting at with that is I would be curious then if like which state they're actually being excited up to, because I imagine if you're going from a UV absorption measurement to a column density of OH, that in there somewhere there would have to be some kind of factor of the population of the lower level of that transition, I'm assuming.
Yeah.
Yeah, and if it is one of the levels of the ground state, it might be difficult to speculate on that. I don't know, that there might be a lot of uncertainties, but I'm not sure.
When there were direct comparisons between the UV and the radio, like the same sight line? You
That
said
would
there
be
was, right?
interesting. Mm.
So this is exactly the same sight line.
Yeah, they are exactly same signal. But there's a difference of 3 orders between
Yeah.
Yeah.
two bands.
Something's really wrong here.
So I wonder where.
Is this published, this comparison?
No,
Not yet. Okay.
yet. We want to apply more observations
Yeah.
with ET, but the proposal was rejected.
So the old observations that you've got the low OH column density from, they're from 1977 and 1960.
The value I used is from the ROF 1996. They have corrected some physical parameter.
And do we understand fully everything they assumed in there? It's like Anita says, if there's some funny assumptions going on. I mean, it's 3 orders of magnitude, it's crazy, and it's hard to see how that would be arrived at. But
So for the
Sorry.
oh, okay. You first.
I was just going to ask the OH. Is that XOH? Is that the OH abundance relative to H2? Is that what that you have here? You have one on each side. There's 2.5 times 10 to the minus 8 on the UV side and 3 times 10 to the minus 5 on the radio side. That's the conversion factor between OH and H2.
Yeah, that's abundance.
Yeah, okay. Just checking because then I'm wondering, is that's derived, like that's what was found as a consequence of those OH? Because they're the same, they're like the same ratio. Yeah.
When you say LTE analysis of the OH, where's the LTE assumption coming in there?
Okay, so I adopt the method of Harris of Carl.
The what, sorry?
So
Carl?
I adopted Carl's analysis in 1968. So
that's why.
we assume that the optic depth of OH of 1667 and 1665 is 1.8. So
hang on. I think that's your problem. Carl's analysis in his old papers is incorrect, I believe. We've talked about this, Ningyu. I think you'll find we have an email exchange from like 10 years ago.
I think you'll find Joe drags it up.
No. I'm not
we do
sure.
not have better. We do not have better solution since we only have 2 main lines.
But you can't assume the excitation temperatures are the same. Is that what you mean? So if you assume that the main lines have identical excitation temperatures, was that your assumption? Or
yes.
not? If you assume that, it was shown by Crutcher in maybe 1979 that by assuming that you have at least an order of magnitude overestimate, usually, of the OH column density. So that's one of your orders of magnitude fixed.
Oh, wow. Yes.
So that's because, as we know from actually your paper and mine, like, so D's paper, D was the first author and you were the second author, and then Heap and then me, that generally your excitation temperatures are offset by about 2 Kelvin, give or take. And you don't always know what direction, but you can show quite on the sort of back of an envelope that if you have a difference of a couple of Kelvin and you assume actually that any differences you're seeing in line strength are simply arising from optical depth differences. Am I getting this right? I'm forgetting how this works, but you can show that by assuming you have the same excitation temperature and using that to derive something about the optical thickness, you're very wrong, because you come out with it being a lot more optically thick than it actually is. And that's because typically it's the 1665 excitation temperature that is higher than the 1667, as we've all measured directly. So that means that you have what appears to be an optical depth, an optical thickness effect. Like you're seeing in that spectrum there, you're seeing that the 65 and the 67 look about the same. And you're interpreting that as an optical thickness effect implicitly by assuming the excitation temperatures are the same. But if it's an excitation temperature effect, where the 65 is just higher than the 67, which it commonly is, then you're going to have a column density that comes out far too high. Did that make sense? I can repeat it.
Yes, you're right. So
So I think
but
yeah, that'll help.
that's the second problem of my theory. So
Yeah.
that option of excitation temperature is very important, but
Yeah.
we cannot without H1 absorption and emission, we cannot have an accurate
Yeah.
value.
That's right, but it's actually more than that, because you can assume an excitation temperature for the main lines and you can compute the column density that way. But if you equate the excitation temperatures as the main lines and use that to derive an optical depth, that's even worse. That's when you really blow out the column densities. So you do better running a range of excitation temperatures from about, I don't know, 3 through to 8 or something realistic based on the statistical distribution of excitation temperatures we've measured, I think. I mean, even judging by the brightness of this thing, look, it's a 0.06 antenna temperature, right? So what's that, 60 millikelvin? That's not a bright line.
Yeah, it's not
That's
bright
not an
line.
optically thick line, and you're assuming it is essentially because you're saying they've got the same excitation temperature, and you're using that to derive the optical depth.
The optical depth is with RT analysis it reaches 1.5.
Yeah,
So
yeah, that's not a 1.5 tau line.
Yeah.
So anyway, that will fix it somewhat. So you might be able to bring it all the way down, actually. You'd need to see.
Can I clarify something? Actually, Joe, you might know this off the top of your head. Because I just while you were talking, I was trying to find because I knew I had a plot of the excitation temperature of 1667 versus 1665. When you say that people find that the excitation temperature of 1665 is higher a lot, is that usually in cases where both of the excitation temperatures are a bit high?
I don't remember actually. All I remember the plot I'm thinking about is in the 2018 paper that Dee led and that you and Hib and I worked on, and also from the sort of handful of measurements that Crutcher made in the late 70s. So it's pretty scattered, and I don't remember if it was happened to correlate with higher or lower excitation temperatures. It can be either way. Like sometimes the 67's higher. It's just sort of as a trend, the 65 tends to be a couple of Kelvin higher.
Yeah, okay. Because just having a look at this plot, I mean, it's just that one data set. It did look like the excitation temperatures of the main lines were very, very similar to one another if they were low. So if they were sort of in the below 8 Kelvin kind of range, it was only really when they got into the 10, 15 Kelvin range that they started to be a departure. But then I only have like 4 data points.
Yeah, I think, again, I don't think it's obvious that there's that kind of trend, but we have very few data points overall, I think.
Yeah, because I wonder so say if you were to do the calculations and say that the excitation temperatures were equal to one another, but then go back and look at what the excitation temperatures would have to be. If they're still something reasonable, if there's still something small like 5 Kelvin.
No, there's something that doesn't work in there though, because implicitly by assuming what you do is you don't know, when you've got an emission spectrum like this, you don't know the optical depth or the excitation temperature. So you can either assume the optical depth is small and then then just assume an excitation temperature, which is what we normally do. Or you can assume that any differences in emission strength are purely set by the optical depth effects because the excitation temperatures are identical. And in that latter case, you can still have a very sensible excitation temperature of like 5 Kelvin, but because you've assumed that these, look at the lines, they're basically the same strength. So you're assuming, oh, this is an optically thick bit of gas because you've departed from the 1:5 to 9:1 ratio. And the only way you can do that is if you top them out and saturate the lines.
Right.
So you're basically assuming that your lines are close to saturated and going, oh my God, look at this incredibly thick column of stuff I have here, because you have not allowed the excitation temperatures to vary by even a smidgen.
Mm.
And if you allow them to vary by a sort of realistic amount of a couple of Kelvin, then you quickly don't have that problem.
Okay. Oh, so
I just post that figure on the Slack channel of the session.
I've got Slack open and I just found that paper. And as soon as I found that plot,
There it is.
it
Yeah.
pops up. Thank you, Heap, for reading my mind. I see what you're saying because it is a little crowded on the left side there, which would be the area where the excitation temperature of the 1665 is higher. But yeah, there's not really enough information there to tell if like what the values of excitation temperature are there.
But I think given how weak this line is, like I'd have to go back and remind myself of my basic radial transfer. But if the line's optically thick, am I doing something stupid? If the line's optically thick, shouldn't we assume that the line strength should be sort of around the excitation temperature? I mean, that's usually how it works. If you saturate out a line, the emission line strength should be around the excitation temperature of the line. And
Yeah, I believe you, but I want to look at the
I'd
equation.
know to check, double check. Heap's got his hand up. Heap, am I wrong? I could be wrong.
No, you're right. So that could be the one order of magnitudes, I think, for the correction.
Might even
I
be
think
two.
another
Might
factor.
even be two.
Two. Okay. Another factor I would say is that because the UV measurements, it tells you about the material between the star and you,
Mm,
right?
that's
And
right.
the OH in radio could be, for infinity path length.
That's a point, yeah. I guess it depends how well you know the ISM in that direction. But you might be right. It could be something behind the star.
Yes, that may happen. So that's why we need more observations to
Yeah.
compare.
Yeah, that's a good point, actually. Yeah. Yeah, it looks like well, at least two of the things that we've been able to think of are at least pushing it the right direction.
Mhm.
But interestingly, it kind of, one of them meant that the radio was a bit better and the other's kind of saying that the UV was a bit better.
This line is so weak. It'd be really interesting to know what the optical depth comes out of if you just assume the CMBs in the background and have a sort of optically thin assumption with a 5 Kelvin excitation temperature or something. We could almost just back of envelope that now.
I think though that the difference between those lines and therefore also how much brighter they could be is kind of within the noise. So I think you'd really have to consider the level of the noise there because the noise could be, suppressing the 1667 and inflating the 1665. Or
you don't care about what they are relative to each other anymore. Like just stick the same excitation temperature into each of them, but don't connect them, right? Just make a small optical depth assumption.
Yep.
Yeah. And just see what you should get. It's such a weak line and it's narrow, so I'm going to ballpark that at 10 to the 14 or below, just from experience. I just can't work that out in my head. Maybe I'll just work that out in my head in a minute. Give me a minute. But don't wait for me. Just like carry on.
Yeah, even just thinking in terms of how common it would be to see an OH column density at 10 to the 16, that just doesn't seem to track with me either, just from experience.
And you need the ratio between the excitation temperature and the difference between the excitation temperature and the continuum background, don't you? That's the scaling factor.
It's in there somewhere, yeah.
But the integral of that line is about 0.04 times about 2, like just by, integrating a Gaussian in my head.
Mm.
So 2. And then it's going to be a factor of order unity out the front. So I'll keep it as, then it's going to be times whatever the hell that constant is. 2 times 10 to the 14. Yeah, right. So I make it 1.6 times 10 to the 13 in my head from the optically thin assumption. So I think it's fine.
Round of applause for Joe. That was cool.
But Ningyu, like, we should check it if you like.
Okay, sure. We can talk
Yeah.
in private.
I think these kind of comparisons are super valuable. I actually never thought of doing them. So
Do we have any more questions on that topic? Because I have a question that's going to change the subject. No? Okay. I'm going to ask a different question. I think earlier in the talk, I think a couple around here, you were talking about the OH abundance and whether or not you'd expect it to change. Here you go. Or whether or not you can measure it changing. Yes, that somewhere. And yeah, it was in quite a few of these slides. I'm wondering, because I'm not familiar with the modeling. I mean, the most I know about the modeling is what I was able to absorb from Sergey's talk yesterday. Is there I guess a simple physical explanation? Like, is there a chemical pathway that's responsible for, or that would be responsible for the change in the OH abundance that you're looking for? Like, is there something that's predicted that we're looking for? Or is it just this would be an interesting thing to find?
Well, yesterday, I think they have a chemical model that can explain this. With denser regions, so the OH forms with a higher will be, I think. Maybe you can look at lower left figure. So that's a result from the Merden. So it's the PDR codes. They have similar trend that OH abundance will decrease with increasing molecular hydrogen column density.
Yeah, and I think you had in the previous slide to this. So
yeah,
excuse me. Yeah, there was also this plot which also showed that kind of decreasing trend. Now the one on the next page seemed, well, I didn't notice if they had any error bars. Oh, they do, okay. It seems relatively, it's hard to say if that's marginal or not. But I'm wondering, is this expected? Is a decrease in the OH abundance with increasing H2, is that expected?
Yes, with fixed parameters, that means fixed UV intensity and column density. That's expect.
Okay. Is there a simple explanation of why? Is it that the OH is consumed in the production of the H2, or is it something else?
The OH will be consumed during the CO formation.
Okay.
So,
okay. That's interesting. Very interesting. Thank you.
Okay, thank you.
I had another question. There was something, it was earlier on in the talk. I think it was on slide 5. where you mentioned that there were some CO dark components. Yeah, so you detected 7 CO dark gas components. So are those individual spectral features that you identified in your 51 sightlines that didn't have associated CO?
Yeah, that's an example. So we
Yeah.
have other
Yeah.
components that
So
it's not
how does that compare to the total number of features that were identified? Is that a small percentage?
which
Is these
uh
7 CO dark gas components, does that represent a small portion of the total detections of OH?
uh it represents the decomposed Gaussian components.
Mm-hmm. So it's not 7 of 51 sightlines, it's 7 of however many, a couple hundred features. Is that right?
Yes.
Okay, okay. That's interesting. So do we have any more questions for Ningyu or any more discussion points? Okay, well then, if you can all join me in thanking Ningyu again for his very interesting talk and the discussion that it inspired. Thank you very much.
Thank you.
I might take a moment before while I still have you guys here and just mention that I've posted something in the all channel about some of the sessions that we're running on Friday. So we have 2 time slots. So the Sydney time, the 1 p.m. and the 4 p.m. Sydney time slots. Those time slots were set aside for if anyone wanted to meet together with people from this group to perhaps plan or propose new observations or new collaborations or anything. So just yeah, keep that in mind when you're attending any of the talks that you go to. If anything gets mentioned of I'd really like to look at that data, or I'd like to use that code, it might be a good opportunity to gather a couple of like-minded people into one of those sessions. All you have to do is just send me a message or something, and we can set that up for you. We can make as many breakout rooms as you need, but with those 2 different time slots. So please let me know about that. So thanks again, Ningyu, and thank you to everyone else who attended. And we'll see you in the next session.